Couple of reminders. Be sure on your bonus quiz too, when you submit it, you've got the name of your discussion instructor written upon, because I'll be collecting the BQ2s here, and I want them to be sorted by your discussion instructor, because that's who these will go to for grading. Now, from point of departure from Friday's discussion class gatherings. Question 2224. The electrochemical cell under consideration, written in standard cell notation, is this. That was from coupling half cells 19 and 39. The discussion classes all proceeded through part 1, and I presume you recognized that half cell 39 is not a standard half cell. So how do you get E0 for this electrochemical system? You've got to consider half cell 39 operating under standard state conditions, for which an E0 value is obtainable. What are the two possible sets of standard state conditions you could consider for half cell 39? Presumably you did this on Friday, so you ought to know what's going on. What standard state conditions mean regarding gases in the system? Partial pressure, 1 atmosphere each gas. Solution species, 1 molar. So if you have a pH-dependent half cell, if you have recognized such, there's 2 possible sets of standard state conditions. What are they? A pH-dependent half cell. What are the 2 possible sets of standard state conditions? pH 0, which is hydronium ion 1 molar, or pH 14, which is hydroxide ion 1 molar. Either one. So if you use or consider half cell 39 under standard state conditions of pH 0, then you're looking at the standard, not the standard hydrogen electrode, but you're looking at the half cell in which oxygen at pH 0 is functioning as an oxidizer. But since this system is operating under basic conditions, I think you're better advised to consider half cell 39 operating at pH 14, where you're looking at oxygen functioning as an oxidizer in the presence of hydroxide ion 1 molar. Information then reads directly from Table 2, the table of half reactions. Secondly, the discussion instructors said there appeared to be confusion on whether or not, when you write the Nernst equation, to get E cell. Because from the Nernst equation, you get E cell. E0 comes from coupling. And you find like species on either side of the net cell reaction. Can I or can I not cancel the molarities of these like species when they appear in the Q term in the Nernst equation? Hydroxide ion numerator, hydroxide ion denominator. Well, nothing fancy about this, and I suspect that what I did last week was to make much too big of an issue of this. If the molarities of hydroxide ion, reactant, product, numerator, denominator, and the Q term are the same, you cancel them. If they're not the same, put in the hydroxide ion molarities and do the arithmetic. That's all. Nothing to it. Hydronium ion molarities, numerator, denominator, same thing. That's all. Now, the remaining part of the question, which one discussion class gathering didn't get to, according to what I was told. If I have 6 molar HCl available, can I operate on this electrochemical cell to make E0 cell and E cell go up? The answer is you betcha. Which half cell do we treat? Anode half cell, cathode half cell, or both? I remind you again that a significant portion of what you need to know about electrochemistry depends upon your ability to use the information in the half reaction table. What does that information mean? Well, look at the information if you didn't do this yet. Although I expect most of you have already done this on Friday. In this electrochemical system, copper is being oxidized to copper sulfide. So copper is the reducer. That transformation takes place most readily under strongly basic conditions in the presence of hydrogen sulfide ion. We already have that established. You don't want to put any hydronium ion in there. The information in table 2 tells you, yes, you can oxidize copper to copper sulfide in the presence of acidic species, hydronium ion, H2S. But that's not as favorable as oxidizing copper to copper sulfide in the basic system. Because if nothing else in the basic system, you're magnifying the effective concentration of sulfide ion. You need to get sulfide ion to make copper sulfide. Acidic system, I'll have H2S. Basic system, HS minus. Clearly this is a better source of sulfide ion. If nothing else, you only got to break one bond here, and sulfide ion's available. Here you got to break 2. We've done a lot of stuff like that in this chapter on electrochemistry. Well, what if I treat the cathode half cell with hydronium ion? What does the E0 information tell you about oxygen functioning as an oxidizer in acidic solution versus basic solution? We've talked about this from even a practical example standpoint. Hey, you up the oxidizing power of an oxidizing system by making the system acidic. It's like 1 molar hydronium ion readily oxidizes zinc, whereas neutral water, pH 7, won't. And the information in table 2 tells you oxygen at pH 0 is a hell of a lot better oxidizer than it is at pH 7 or pH 14. So treat the cathode half cell with hydronium ion. Clearly then, for this system to operate, you've got to have physical separation of the 2 half cells. Because if you start dumping hydronium ion in there and you don't have physical separation, complete physical separation of the 2 half cells, well, then the hydronium ion is going to get into the copper half cell as well. This refers to one practical problem that electrochemists deal with if they're battery designers. How do I design these batteries? Because simple batteries are not designable. So as to have complete physical separation of the half cell components, like the car battery, or single A, double A, triple A batteries, stuff like that. In any case, enough on that. We go to question 2225. Again, many of you have looked at this, but so what? It's good to be sure you're on top of this. We have reminded you, when we first started to talk about the Nernst equation and its use, that one of the principal uses of the Nernst equation is to calculate equilibrium constant values. So look at Table 2 if you've not yet done this. And tell me which half cells need to be coupled if, on application of the Nernst equation to the net cell reaction, I want to be able to calculate KSP for this stuff. Now, at the minimum, to be able to answer this, you have to remember how the KSP equilibrium constant is defined. It's defined as the K value for the reaction in which the semi-soluble stuff dissociates into its ions, or for the reaction in which the ions come together to make the semi-soluble stuff. What is it? Which way? Hey, when we talk about Ka, you have to know what that means. Some of this language you just got to know. Ka, the acid in question reacts with water, makes hydronium ion and the conjugate acid. Can I write that reaction in the opposite direction, and is it still a legitimate equilibrium? Yes and yes. But if I write that reaction in the opposite direction, I got 1 over Ka, not Ka. So for the KSP consideration we just put to you, if I write the reaction one way, I got the K values KSP. If I write it the other way, I got 1 over KSP. Which way is it KSP? This dissociates into its ions. So let's write that first, in the event that you've not yet done this. And then answer the question, what ions must react with each other to make this stuff? What are the ions that react with each other to make this stuff? The ions. Tell me the formulas for the ions. Fe3 plus? First of all, this contains iron in what oxidation state? +2, not +3. So what +2 ion of iron do we need to consider? It's in the table. In water solution, we shall well expect these multi-charged metal ions to be present as what kind of species? Hydrates. And unless we tell you otherwise, how many water molecules of hydration per ion? How about that? Now, at a glance, if for nothing else, because of your experience with chemistry in 46 laboratory, if you're going to make a gelatinous hydroxide, which is what this is, does it not seem to be the case that you have to react the metal ion with hydroxide ion or a source of hydroxide ion? Nothing fancy about this. So those are the ions which get together to make this stuff. Of course, in this KSP business, we're writing them as products. So we don't as yet have an equation, do we? Because when this reacts with this, what kind of chemistry occurs beside precipitate formation? What is it? Acid base. Hydroxide ion buys H plus from one of these hydrated water molecules and converts that hydrated water molecule by H plus extraction to a hydroxide ion that's stuck on the iron. Done. So when we protonate two of these, we make it two water molecules. They're there. Now, which half reactions do you couple to get this thing as the net reaction? Look at the table. Does 15 and 22 get the job done? Now, to be sure you can operate on the Nernst equation to get the KSP value, again, you probably did this, but let's try to be sure. There it is. E cell is E0 cell minus 0.059 V divided by 2, the number of electrons transferred. For the half reactions involved in this system. Now, I don't remember what the E0 values are. You look at the table, you tell me. What's the E0 value for 15? 0.88. Which of these half cells got reversed to develop this equation?
15.
So this is minus 0.88. And 22 is as written. What's E0 for 22? 0.44? Is that correct? Okay. So E0 cell is minus 0.44 volts. This shouldn't surprise you at all. Because from a spontaneity standpoint, is this thing under standard state conditions a spontaneous reaction? Yes or no?
No.
Heck no! These things react with each other like gangbusters to make this stuff. So the tendency for this stuff to dissociate is damn small, as reflected by the fact that its KSP value is damn small. That's what these KSP values tell you. You're looking at reactions which are not spontaneous under standard state conditions, not even close. Because those things are pretty stable. So for this reaction going this way, delta G0 is big in minus, but going this way, it's big in plus. All right? We got everything we need so far except E cell. What's E cell? If you can't write down E cell, you can't answer this question. Because right now you got two unknowns. You want to get log KSP, and to do that you need E cell. What's E cell? Louder.
Zero.
Zero. This damn thing's in equilibrium, right? You're calculating an equilibrium constant. It's all based on understanding. Have I said that once or twice this term? 1,000 or 2,000 twices? That's where it's at, folks. Okay. KSP's, I think, in the notes written. Sometimes 10 to the minus 15 or something like that. I mean, you calculate a KSP and you get 10 to a positive power, you get something wrong. These things are very, very stable materials, these semi-soluble salts. So you know the 10 is going to be to a negative power on the KSP value. All right? Now then, 26. For the two non-standard half cells that I have listed in the table. Bear in mind that these half cells are included just to support the recognition which we have reflected on. How oxidizer strength changes as a function of pH, how reducer strength changes as a function of pH. In particular, for the information in Table 2, hydrogen is considered as a reducer, and oxygen is considered as an oxidizer. And as we have already recognized, the power, the potency of a reducer increases. How? Based on pH.
As pH decreases.
More, to make the reducer more powerful. More basic. More basic the system, the more powerful the reducer. Look at Table 2 information for hydrogen as a reducer. Look at hydrogen as a reducer at pH 0 and hydrogen as a reducer at pH 14. It's a much more potent reducer at pH 14. pH 0, you're looking at the standard hydrogen electrode, where the electrochemical potential is the defined value of 0, our reference point electrode. Hydrogen at pH 14. What's the E0 value? What's the table tell you?
0.82.
0.82 volts. Hey, the tendency of hydrogen to be a reducer went up very much by putting in the presence of hydroxide ion. How about oxygen as an oxidizer? We've been talking about that for question 22. Question 24 in chapter 22. Pardon me. So enough said on that. Now for these two non-standard half cells, specifically 23 and 39, let's take a look at this one, where the E cell value is plus 0.41 volts. How do we get that? Nothing fancy about this. This is an E value, right? Not an E0 value. What device do we use to get E values? What is it called?
Nernst equation.
Nernst equation, right? That's what we use to calculate E cell values. Well, this is a half cell. So what? We're going to apply the Nernst equation to a half cell. So we'll write E cell equals E0 up E half cell. Let's get the notation right. E0 half cell minus 0.059 V over 2. There's N times the log of Q. Here's Q for this half cell. Hydronium ion product, molarity squared, divided by the partial pressure of hydrogen gas. Now, what is the non-standard component of this half cell system? What is the non-standard component of this half cell system? Do you see the information in Table 2 tells you this half cell is considered at pH 7.00 when we have the E cell value of 0.41 volts? See that? So what's the non-standard component of this half cell?
Molarities.
What is it?
Molarities.
Well, don't say molarity.
Or molar.
Hydronium ion concentration, okay? What is the hydronium ion concentration at pH 7.00? 1.0 times 10 to the minus 7. 1.0 times 10 to the minus 7. All right? This is still 1.0 atmospheres. If this too was non-standard, we'd have to tell you. I mean, I can change the partial pressure of hydrogen with my gas valve that's connected to the system to anything I want. But if we're changing that too, I got to tell you. All right? So this is 1 in the denominator. I have to pay attention to it. What's the log of 1.0 times 10 to the minus 7 squared? What is it?
Negative 14.
Negative 14. And if you need a pocket calculator to get at that, something's wrong. You don't understand fundamental log considerations if you need a calculator to do that. So you got a minus 14 divided by 2, minus 7. And then you got a minus times a minus, which makes a plus, doesn't it? Now this is about 0.06. Do you agree with that? What's 7 times 6? 42. Well, this is 7 times 0.059. So are you surprised that you get 0.41 instead of 0.42? Because this is 0.059. All right? What's this value? Because here is the half-cell reaction I'm considering. And I'm going to consider this to get an E0 value. I'm going to consider this at what pH? What pH? To get the E0 value. What pH? 0. And what is the E0 value at pH 0 for this? 0. There you are. Done. You do the arithmetic, you get 0.41 volts. All right. Concentration cells. Interesting cells. Interesting cells because they show you that a metal does reduce its own conjugate oxidizer. Or put another way, a conjugate oxidizer oxidizes its own conjugate reducer. Or an oxidizer oxidizes its own conjugate reducer. So let's take a further look at the concentration cell, which is discussed in the notes. Again, on expressing this concentration cell in standard cell notation, we recognize that the anode copper is at the left and the cathode copper is at the right. Which means this copper ion is being produced by oxidation, and this copper ion is the oxidizer. This is the copper ion that's getting reduced. So I'll draw a picture. Since my artwork is favored by artists throughout the world, it's absolutely beautiful stuff. Ha ha ha. We shall imagine again this is a voltmeter. And in each half cell compartment, we got hydrated copper ion floating around. And some non-reactive anion, probably sulfate ions. So let's call it sulfate ion. And of course, water molecules all over the place. Now, the net cell reaction shows copper metal reacting with hydrated copper ion to make, guess what? Copper metal and hydrated copper ion. So let's talk about the thermodynamic driving force for a concentration cell. We'll start with delta G0. Is that the thermodynamic driving force for a concentration cell? What is delta G0 for a concentration cell? Well, what's E0 for a concentration cell?
0.
0. Delta G0 can't then be the thermodynamic driving force, can it? I mean, you got copper plus water molecules becoming hydrated copper ion and 2 electrons. You write down the standard electrochemical potential. Then the other half fraction is the same half fraction in the other direction, which means you got the same E0 value except the sign has changed. So when you add up these E0 values by coupling, you get 0. So delta G0 isn't making this concentration cell do anything. So it's got to be delta G0R. Now delta G0R is equal to, beside minus NFE, change in enthalpy for the reaction, minus T delta S for the reaction. How about this? Can delta HR be part of the driving force for a concentration cell? There's our net cell reaction. Can delta H for this reaction be part of the driving force? How could it? Whatever bonds are broken, exactly the same bonds are reformed as you get the products. So this can't be anything. That leaves one puzzle part. What is it? That's the driving force. Thermal driving force is called entropy of mixing. Consider 2.0 molar copper sulfate solution and 0.010 molar copper sulfate solution. You could easily prepare these in the laboratory, should you desire. If I take a beaker, and in the bottom of the beaker, I put 100 milliliters of 2.0 molar copper sulfate solution. Okay? And then I pour very carefully so as to minimize agitation and mixing. I pour 100 milliliters of 100th molar copper sulfate solution on top of the 2.0 molar copper sulfate solution. You remember what I done? No, nothing fancy. I got a beaker, put 100 milliliters of 2.0 molar copper sulfate solution, then very carefully I add another 100 milliliters, but this time of 100th molar copper sulfate solution. Then I walk away from the beaker. I go to the nearest McDonald's. I want to get a case of stomach cancer. Every time I go into McDonald's, as if I had a bomb. No, that's not true. Maybe a gas bomb. Bad smelling to make the people get the hell out of there. Yet I see people pouring profusely into this place of ill repast, day in and day out.
It smells pretty bad already, too. What are you doing?
McDonald's. It doesn't please me when I go to Saigon and I see McDonald's in Saigon. It's interesting, really. From a matter-of-fact standpoint, the only thing in Saigon which appears to me to be communist are the hammer and sickle flags they have flapping around the streets. After that, forget it. The major construction in Saigon is all supported by American oil companies. They're a real communist operation. Burger Kings, Pizza Huts, they're taking over the place. I don't get it. But communist, I don't think so. In any case, forget that part of the puzzle. I'm not going to McDonald's. I'll walk around, I'll take a 2-mile hike. This is good for me. Maybe 20-mile hike would be better. Okay? And I come back. Remember how I put this system together? If after a couple hours standing, I analyze this system, do you think at the bottom I'll find strictly 2 molar copper ion and at the top I'll find strictly 100th molar copper ion? These are liquid systems. Are liquid systems dynamic? You betcha. If I let this beaker stand long enough, for a period of time called infinity, so all kinetic considerations are out of the way, and I analyze the copper ion concentration, will I find copper ion concentration gradients? Will I find in one part of the beaker 2 molar copper ion, another part of the beaker 1.5 molar copper ion, another part of the beaker 100th molar copper ion, another part of the beaker 1,000th molar copper ion? Will I find that? No. What will I find? I'll find the copper ion concentration has become uniform throughout, and it will have a value of about how much, given that I put 100 milliliters each of these solutions. What value of copper ion concentration will I eventually wind up with? I'm listening. Shall we go back to our demonstration of 1 molar acetic acid put together with an equal volume of deionized water, and I treated with methyl orange indicator, and I asked you to predict the colorimetric result? Now, I got all kinds of funny predictions. If I run this system, if I construct this system, what molarity of copper ion will I wind up with, practically speaking? What? I'm listening. What? I'm listening. All right, I write the answer on the board. I'll put it in the beaker. There it is. 500 points if you want to see it. 1,000. 2,000. This is like mixing deionized water, 100 milliliters, with 2 molar copper ion. You're diluting the 2 molar copper ion to 1 molar copper ion practically. You agree with that? Hey. This is very close to 0 molarity compared to this. Nothing fancy about this. All right, now let's go back to our concentration cell. These are the solutions we're going to use from which to fabricate this concentration cell. So we're going to have an election. In this half cell, you can put 2 molar copper ion or 100th molar copper ion. Now, if I put 2 molar copper ion in here, then by default I put the 100th molar copper ion here. Or I could put the 100th molar copper ion here and the 2 molar copper ion here, right? There's only 2 possibilities. Okay? So we'll call this half cell A and this half cell B. Two molar copper ion. How many of you want to put it in half cell A? We got 1.5 votes. We got 2 votes. Well, that means 2 and all else. How many of you want to put 2 molar copper sulfate solution in half cell B? Well, you don't want to put it in A, you don't want to put it in B. So where the hell are you going to put it? Huh? You got to make a vote. No vote, you can't take this exam. And again, there'll be well over 300 points earnable. So let's try again. You got these 2 solutions. You got to put 2 molar copper sulfate solution in A or B, and then by default you got to put the other solution in the remaining half cell. You understand? Nothing fancy about this game. We'll start again. How many want to put 2 molar copper sulfate in the first beaker, A? 1, 2, 3, 4, 5, 6. All right, we're up to 6. How many want to put 100th molar copper sulfate solution in half cell B? Everybody else raise up their hand. You can't really have your 20.
Just ask the same question.
I did? Oh. Pardon me. How many want to put 2 molar copper sulfate solution, well, not in A, but in B? You know, first I asked how many want to put it in A. Now I'm asking how many want to put this solution in B. There. Okay? Everybody else. Okay. All else. Now then, This means that more people decided to put the 2 molar copper sulfate solution here than they did here. Okay? So here we go. 2 molar, 100th molar. Now comes the $64 question. If this is the way I rig up this electrochemical cell, will the electrons flow this way? Or will the electrons flow this way? Which way? What I'm really asking you is, by putting the 100th molar copper ion here and a 2 molar copper ion here, am I going to keep this as the anode half cell? Will this be the anode half cell, or will it now be the cathode half cell? If I put the 2 molar copper ion here, will this be the cathode half cell, or will it now be the anode half cell?
The anode's on the right.
I got to vote for the anode on the right with the right containing 2 molar copper ion. Now what happens in the anode half cell? Oxidation occurs, which means in the anode half cell, for this concentration cell, I'm oxidizing copper to hydrated copper ion, right? Which means if this is the anode half cell, the copper ion at 2 molar is going to get more concentrated. You really think that's going to happen? I don't think so. So if we put the less concentrated copper ion here, this will be the anode half cell, and this will be the cathode half cell. So this will keep with our standard on the board representation of an operating electrochemical cell. The anode half cell system on the left, the cathode half cell system on the right, and the electrons will flow this way. Hey! But I could just as easily have put the 2 molar copper ion here and the 100th molar copper ion here. But the electrons would then go this way. And this would be the anode cell compartment, and this would be the cathode cell compartment. Because you know doggone well that what's going to drive this is tendency toward concentration equilibration. So when does this electrochemical cell, this concentration electrochemical cell, when does it shut down? It gives us usable electrical energy until what condition is achieved?
Equilibrium.
And what is equilibrium going to be established by?
When the concentrations are equal.
When the concentration of copper ion becomes exactly the same in each half cell, about 1 molar. Bingo. Goody, we got that. All right. Now a few words on galvanic protection. I suspect most, if not all of you, have heard about this. These oil rigs that you know are present in the Gulf of Mexico. There's a bunch of these off the coast of Vietnam, run by these big, rich oil companies that I talked to you about. Maybe I mentioned I went to the top of the Texaco Tower in Saigon. 80-story building. Go up there, you know, observation deck, you can look around. It's a really nice building, fancy. You know how long it takes to go from the ground floor to floor 80? With the fastest elevator in Southeast Asia? 14 seconds. That's not bad. And you don't even know you're moving. You're in there and wait, door opens, there you are. It's amazing. You feel no sense of, I mean, I don't know if you've probably never been on older elevators. I mean, when I was a kid, and Mom would take me to a department store or something like that. You got an elevator, go from the first floor to the second floor. You, boom! What happened? And boom! And you could feel the thing. Not there. There you are. Oh, isn't that nice? Okay, interesting. The most commonly protected metal by this method is iron. That's what you're protecting on these oil rigs. Because they got, for example, iron posts on which they stand, stuff like that. You got to keep that stuff from rusting. Now, what do? Let's imagine this is an iron bar. If I take this iron bar and fuse to it a zinc bar, I don't need to cover the iron bar surface-wise. I just got to have the zinc in contact with the iron bar. Number one, as the half reaction information in our table tells you, zinc is a considerably stronger reducer than iron. Which means if I take my iron bar, when it's connected to the zinc bar, it exposes it to an oxidizing atmosphere. The zinc gets oxidized, not the iron. But if I don't have the zinc in contact with the iron, say iron in presence of moist air, water, oxygen. The iron rusts readily. It rusts readily, particularly if the system is basic, because of the extreme thermodynamic stability of this stuff. Now we're getting kind of close to the end of the pipeline for 46 laboratory for you folks. How many of you expect to do assignment 10? The more the merrier. Whatever points you make in assignment 10, just add it to your total point score. And like the syllabus tells you, when you make 900 or more, you got your A. Hey, so in assignment 10, you'll prepare this stuff. You'll examine some of its properties. It's very readily formed, provided conditions which allow its formation to exist, because it's so damn stable. I'll give you a clue. If my memory's right, exam 3, one of the extended questions on electrochemistry will invite you to calculate KSP for this. I can tell you that. I can tell you the answer. Who cares? Because you're going to have to do it by the method that I ask of you on the exam. So, I want to prevent the formation of this. Not only is it very stable thermodynamically, it's very poorly stable structurally. So when I form this goop on the surface of iron, this falls right off and it keeps on exposing base metal iron to oxidizing conditions. So you oxidize more iron to this hydrated iron hydroxide called iron rust. Common formula given in books for iron rust is Fe2O3.XH2O. Because it's not really a stoichiometric material. We use this as a stoichiometric formula that we invented for your work in laboratory. Okay. Better like this because I don't know how many water molecules are in there. So I want to stop the formation of this. Not only because it's so stable and has a strong tendency to form, but because it has no structural integrity. So if I form it, it falls off. But zinc, which is more readily oxidized than iron, when zinc oxidizes, I make zinc rust. Call it this. This has a much greater thermodynamic stability. I mean, not only is this more thermodynamically stable, pardon me, this has a much greater structural stability. So if I make this on the surface of zinc, and the zinc, for example, is wrapped around the iron, hey, then oxidation shuts down. Because that's stable, it stays there. Remember we told you when we did some illustrations of zinc and copper ion and zinc ion, how would we design an electrochemical cell using these materials? At the start of our conversation on electrochemistry, we said, well, if you look at the E0 information, you really see that zinc does reduce water. But on the surface, you make a molecular layer of that stuff, and that stuff is stable. It stays there, just like here. If in the presence of moist air, you oxidize zinc to zinc oxide or zinc hydroxide, the stuff stays there. It doesn't fall off, so it stops the oxidation process. So that's an illustration of galvanic protection in action. I take a metal that I want to protect. Most commonly, that's iron, because so much construction is done with iron because of its structural integrity, base metal iron. And I put it in contact with a metal that's a stronger reducer, a metal that is therefore preferentially oxidized. And once this metal, which is preferentially oxidized, is oxidized, then I can shut down the redox reaction. Now, I think what they do, for example, with these oil rigs, I'm pretty sure they use magnesium strips, much stronger reducer even than zinc. And I think what they do is they change out the magnesium because magnesium is pretty cheap. So they got magnesium in contact with iron, and after the magnesium gets oxidized, or however, I don't know the mechanics of it, you could look it up on the web. They keep replacing the magnesium strips that's in contact with the iron with fresh magnesium strips to keep these big iron posts stable, because that's what the platform's sitting on. You don't want that turning into rust, the platform goes into the drink. Enough on that. Now then, the last issue of consequence in chapter 22 is derivation of E0 half cell values for new half cells, or at least half cells for which I may not have the E0 data readily available. Let's look at the case that's in the book, because I think it will serve readily to illustrate such. First, we take a look at iron. Considered to be oxidized in the presence of water to make hydrated iron plus 2. For which the half cell potential is plus 0.44 volts. In fact, this was one of the half cells we had to consider coupling to get the KSP for that iron 2 hydroxide we looked at a short while ago. Okay? Now we're going to look at another half cell. That's in table 2. where hydrated iron plus 2 is oxidized to hydrated iron plus 3. And that's minus 0.77 volts. Now, this means if I'm going to oxidize iron to make a hydrated metal ion of iron, which hydrated metal ion will I expect to make? Two plus or 3 plus? Which one?
3.
Oxidizing iron 2 to iron 3 hydrated metal ion has got a minus potential. Right? So if I'm going to oxidize iron to a hydrated metal ion, this suggests thermodynamically I'll make the plus 2 oxidation state, not the plus 3 oxidation state. I mean, what we want to do is talk about the chemistry of this as we go through the analysis. Stuff like this will be part of exam 3. Now, what happens if I put these two together? I add them up. I got a new half cell. A new half cell obtained by combining these two component half cells. But in putting these two together, I got a new half cell, not a net cell reaction, a new half cell. The question is for this, what's E0? Statement. For this new half cell, E0 is not obtained by coupling these E0 values. Now there's a detailed explanation of why you cannot do this to get E0 for the new half cell. It's in the notes. You take a look at that. But in so many words, the coupling process works only to get E0 for the net reaction when you have no net electrons in the net reaction. Well, here you have net electrons because this is the half cell. So I can't go through the E0 values to get E0 for this new half cell. How do I get the E0 value? I have to go through energies. So statement. To get E0, let's write down new half cell. Must go through delta G zeros because energies, but not potentials, are additive. Now tell me, before we operate on this, to get E0 for this new half cell, the ones that's been derived by adding up these two component half cells, how do I expect E0 for this new half cell to compare to these values?
I think it should be less than, because Fe3 plus is a lot less thermodynamically stable or favorable.
Well, you got to be a lot less. You got to make a comparison. You can't stop there.
Oh, then the 2 plus.
So you expect E0 for this half cell. Before we get at it, we're going to get at it. To compare how to this number?
Less than.
Less than. But what about this number?
That's negative.
Well, this number is negative.
Yeah.
But do you expect this value
I think it should be
greater than this one? This one's going to be intermediate between these someplace.
Yeah.
So what is this value? All right. So before we do the arithmetic on this, which we're going to do tomorrow, We've written this down. But now I'm going to add something to this. However, and we'll do this part 2 tomorrow. However, the best way to get E0 new half cell is through delta G super zero sub F information. For example, such as we find great quantities of in table 1. Do you remember using delta G sub F super zero information before to do something with it? Like, for example, to get Kas for strong acids. So now we're going to use delta G sub F super zero information to show you the simplest, most direct way to get E0s for new half cells. So we'll pick it up from this point tomorrow, and then we're going to dive headlong and headstrong into chapter 23. Read that stuff in chapter 23. Important.